Okay, thank you very much for the introduction and also for the invitation to present our work on surface acoustic waves of photonics. I'm at the other university here in Valencia, in the Material Science Institute, and we are currently part of European network, SolTrain. It's an international training network in which also VLC Photonics is associated partner. And most of the things I'm going to show, I will try to be fast and skip most of the details. But basically, we want to work on devices that we feed light at some point, and the response of our device is changed by the acoustic waves that we propagated in our structure. So the outline of the talk is, firstly, I would start with a brief overview on surface acoustic waves. I assume that most of you are not familiar with the topic. Then I'll basically discuss two kinds of geometries. The first one are devices that operate with light out of the plane. These are not so much into integrated photonics, but nevertheless are pretty fun, in my opinion, let's say. And at the end, I will discuss a lot of in-plane devices that are more likely to be used in integrated photonics. Okay, so what are these surface acoustic waves? First of all, the word surface here is not really just the interface with air, but it's the region that actually penetrates a little bit into the substrate. But as a rule of thumb, basically, this is a simulation of an acoustic wave. So you see the acoustic wave penetrates inside this is the depth of the sample. So it penetrates into the depth, but basically the acoustic power is attenuated within one acoustic wavelength. Okay, this is a plane wave that propagates. And that's the basically definition of surface acoustic waves. It has an exponential decay towards the bulk. It can be generated using a RF signal or pulsed laser. Typically, you have a speed of sound in the solid of kilometers per second. And this is a technology that is very well known and developed. So in each mobile phone that we have, more or less we have, I think the last iPhone has something like 20 of surface acoustic wave devices, filters. And also in the field of optics, it's well known, they are used for Bragg cells. In our approach, you usually use the electric excitation, use radio frequency. Okay, we take advantage of piezoelectric materials. Then we can just have interdigital transducers as depicted here. So you have this kind of comb-shaped electrodes. And then you apply radio frequency, and we generate this acoustic wave in our substrate. This is a picture of an actual device. This is a special one that has a geometry that generates a collimated beam. And one nice feature of this surface acoustic waves is that you can actually map the acoustic field from the top. So this is not a simulation. This is a real experiment. Okay, measured by interferometry, and we can see the acoustic beam propagating out of our transducer. These are the typical dimensions that I'm going to talk. This is not the limit, but it's the limit in our approach because it's close to the limit that we can fabricate using optical lithography that have features smaller as 700 nanometers. It gives a acoustic wavelength close to 6 micrometers. Okay. So what can we do with these surface acoustic waves? The acoustic modes that we use are typically Rayleigh waves, and since it has a piezoelectric potential, the materials are piezoelectric, The first effect that has is that it bends the conduction and valence band of our semiconductors because of this electric potential that is also sinusoidal. But on top of that, there is the deformation potential that since we have regions of tension and regions of compression in our sample, the band gap of our semiconductors are also locally changed. So this is another effect that can be used. Okay, but in the case of photonics, probably the most important effect is that due to the elasto-optic interaction, we change the refractive index of our sample. Then to combine source with photonics, then as I mentioned, we use this elasto-optic interaction. This is well known, and this is the principle of operation of these Bragg cells. But if you have systems that rely on the geometry, on the dimensions, such as photonic crystals or semiconductor microcavities, also the strain that is part of the wave can be very important. And actually in the view graphs I'm going to show in a minute, this effect is even larger than the refractive index modulation. On the technological point of view, it's interesting because it's compatible with almost every material. It's monolithic and it's very inexpensive. Someone may say, okay, but systems like SOI, they are not piezoelectric, so how can you say that they're compatible? But we can just put on top of the system a piezoelectric overlay, and then you can generate our acoustic waves. Okay. Then our out-of-plane geometries. This is probably the first system that have worked. And just a planar microcavity. Okay, so we have a Bragg mirror on the bottom. Okay, this is our periodic arrange of layers with contrasting refractive index. You have to build them with a particular thickness. And then we have, the material should be transparent at this, at a given wavelength, but because of this, the interference created by this periodicity here, we have a region of high reflectivity. And we have another Bragg mirror on top, but there's a layer here that has a different thickness. And this generates a mode inside this region of high reflectivity. And this is what we call the cavity mode. Here we have a broader view. So this is the plateau of the Bragg mirrors, and this sharp line here is our cavity mode. Okay, so if you look at the expression for the frequency that we expect for this cavity mode, it depends on the refractive index and also on the thickness of this layer here. And then as we apply a surface acoustic wave, so you see that this dotted line here shows the profile of the acoustic modulation. It's stronger, you cannot see here, but it's very strong at the surface, then it decays, but it has, we have to match our geometry to have our cavity layer in a region where it's meaningful, the modulation. So here it's more or less okay. And then we are going to have the strain, and also the elasto-optic interaction will change the refractive index. And as a consequence, this frequency here is going to move around. Let's see if the video works. Okay, as I was afraid that it's not in the pen drive. Okay, but this is an experimental. This is also experimental, but this is another measurement of the same cavity, but with a very large aperture objective, so that we have a distribution of angles, and this is why the cavity is a little bit broader, but the video would show that this cavity mode would walk around here as the acoustic wave passes by. And I go a little bit fast here, but the idea is that if we probe several periods of the acoustic wave, okay, now we add an additional periodicity in the in-plane direction. And if you look at the dispersion of this frequency, so the resonance frequency is just for light that comes from top, like this. If we start to inclinate the light like this, then there is a dispersion curve that is more or less parabolic, okay? And now because we have this additional periodicity here, this dispersion starts to fold in a mini Brillouin zone. And then the dispersion changes as we increase the acoustic power. These are simulated results. And these are the experiments. So we basically can see most of the features that comes out of the simulation. And what we are doing here is now to create an optical superlattice in this in-plane direction that is just produced by these surface acoustic waves. Okay, I'm not going to all the details, but it's also nice because if you apply light that comes at the Bragg angle, okay, so you can have Bragg diffraction, but not just a regular Bragg diffraction, but with a very, very high diffraction efficiency. We got close to 50% of the light that is diffracted back, okay? And this is also works like a device so that if you don't have acoustic waves, so you just turn off our generator, you have no light that is coming back, and you switch on, and you have 50% of the light coming out of this direction. We applied the same concepts to a more complex system, that is, we embed a quantum well inside of our cavity. So now that we have not only photons, but also the excitons that are trapped in this cavity. I'm also skipping all the details, but this is the signature of a microcavity polariton. That is when these photons and the excitons are strongly coupled between them. So you have this anti-crossing over here, and we have two different modes now. And if they are coupled, we don't talk about cavity or exciton modes, but just lower polariton and upper polariton branches. And we can also fold the dispersions like this and create a Polariton superlattice that is similar to the one that we created for photons. But this is very interesting because these Polaritons are actually, they can actually condensate as a Bose-Einstein condensate, and it has a lot of interest. And this is a field, the investigation of this Polariton superlattice that started after our work. Perhaps more interesting and related to the photonic or integrated photonic devices are geometries where light propagates in the plane of the device. So I'm going to show, give an overview of many things that we have done. Some of them may seem a little bit exotic here, but nevertheless. So here is more or less the opposite to the things that people are interested in when they are talking about photonics. Here we actually use the photons to change them to electrons, and then we manipulate the electrons and we get back the photons. So the idea here is that we have, for instance, here, this is a photoluminescence experiment where in is the place where we have a laser spot focused. So here we have our excitation spot, okay? And then what the surface acoustic wave does is capture the electron and hole pairs that are created in this position and transport them to a remote location. In this place, we put a metallic stripe, and the piezoelectric potential is quenched, so the carriers that are transported over here have to recombine and emit luminescence there. Okay, so this is a picture showing here that we come with photons here, they become electrons and holes, we separate them with the acoustic wave, transport them to a remote location, and what is nice is that we can put an orthogonal Sol beam here and actually switch the direction of propagation so that the light does not go out here, but out there. And there was also another work where we demonstrated, this were performed at 15K, but we have some work showing that this also works at room temperature. Of course, this cannot really be done for integrated photonics, but it's interesting for instance, spintronics, because we can keep track of the spin of the electrons, okay? And then we have the two states that are necessary for spintronics. Another possibility is to have single photon sources. Okay, this is not really in plane, but we can easily couple that with, or think of ways of coupling that with in plane devices. So in this experiment, we have a nanowire with a quantum dot on the tip. And we do more or less the same thing in the previous slide. So you have a laser spot at the bottom of the nanowire. This creates electron hole pairs at this extremity. And the acoustic wave, what does is transport these carriers to the region where you have this quantum dot, and they are forced to recombine there. So if you do it properly, we can do in a way that we transport single electrons or single holes, and the first one is trapped there, and it waits for instance, if we carry first the electron comes, is trapped there, and waits for the hole to come next, and then recombine and emit a photon. If you do it in the proper way, we can have very few photons emitted, right? Okay, in this case here, we have more or less if I remember right, it's something like 10 to 12 photons recombining at the same time in this anti-bunching experiment. And from here to the end of the talk, I'm going to talk about things that are probably more familiar to you, that are approaches using source acoustic waves, but to drive acousto-optic devices that are more, let's say, conventional, right? So there are some ideas to modulate photonic crystal microcavities, like this one here. So the frequency of this resonant cavity is very much on the refractive index of the material and also on the dimensions here. And then the acoustic wave, when it comes, moves the frequency up and down in a similar way as the one that I showed for the in-plane configuration. And other approaches modulate optical waveguides. So there are proposals to make frequency shifters using acoustic waves. And I want to call the attention for this one, that is the one that we are going to discuss from now on. That was first proposed a while ago to modulate, this is just a March-Zehnder interferometer. So you launch an acoustic wave perpendicular to the, parallel to the wave fronts are parallel to the propagation here, the arm of this March-Zehnder. So we modulate the refractive index of this waveguide, and they would place here at the center of the March-Zehnder something to absorb the acoustic wave, so you don't touch this other arm. And then controlling the acoustic wave here, you have interference there, and you have a modulator. So what we have done was to propose a system where we modulate both arms at the same time. So here you probably can see better. This is our device. So you have, these are the two waveguides, okay? But we place them in a particular way that they are filling opposite phases of the acoustic wave. So we rely on the phase coherence of the acoustic wave, so that when the arm is, the refractive index is going down, the other one is going up. So we can have, we don't have to put absorption here and use all the acoustic wave to modulate both arms at the same time, okay? These are more or less the system is on gallium arsenide. These are the dimensions, and we made it by photolithography, plasma etching, and so on and so forth. And these are the results we got. So the white line here is the transmission when the acoustic wave is off. So you have just a constant light coming out. And when you apply the acoustic wave, we start to have these oscillations. And for high acoustic wave powers, we have almost 100% modulation. And actually, you see that this curve here is not very symmetric. This is because we have higher harmonics coming in. But basically, it's a very short, relatively short active region on the order of 15 microns. That is the aperture of the acoustic transducer, and modulation close to 100% and gigahertz operation. So it's a nice compromise, and this is probably why it was the cover of Applied Physics Letters at the time. The thing is that this is not really, I wouldn't say useful, but there is a problem because the bandwidth is very, very narrow because it's fixed by it just works at one particular frequency. Okay, if you go out of this frequency, it doesn't work very much. So we keep working on other approaches. So this, for instance, this one is a different device where you have a two-port modulator. So we have now MMI here. And instead of having light on and off and losing half of the light, now we have two ports. And what we do is we switch the light from one port to the other as the acoustic wave passes by. So we have this two-port modulator. Very efficient also. We almost don't lose light. And you see this, this is for very, very tiny modulation. This is very high. High modulation, that's when works at more or less 100% efficiency. But if we go up in frequency, we can have even the second or third harmonics coming up, okay? This is experimental points, and we can actually simulate that pretty well. We generalize that for the case of any output ports and any input ports. Actually, if it doesn't, in the case of this work, it doesn't have even to be an acoustic wave, but if we apply delays on or phase shifts in the light that is propagating at different arms, if you do a combination of these phase shifts, we can actually have an N by N MMI being switched in different outputs over there, okay? So also without going to the details, these are different combinations of the phases that you have to apply in this different waveguides for a 5x5 modulator, and this is what we expect for the outputs as a function of time, okay? So you see that light goes, instead of coming out at one port or all the 5 ports at the same time, it just switches from one port to the other as the times goes by. And we have another approach also using MMIs, that is instead of modulating okay, let me see, like this geometry here where you modulate the waveguides, okay? And we have very large MMIs outside our active region. We thought that we can actually try to modulate inside the MMI. So we have some simulations where you can actually modulate a particular plane of inside the MMI using a transducer that actually focuses the acoustic wave in a very narrow beam. And actually this is a little bit outdated because now we have the Spanish patent is already granted, so we have a different number here, but I didn't update the slide, sorry. And in this way, we can actually have multiple ports coming out of the MMI, and we can switch the light between two adjacent ports using our approach, but it's much smaller now because we actually modulate inside the MMI. And the last thing I wanted to mention is to try to achieve tunable AWGs, phased array waveguides using acoustic waves. So the idea here is that we come with many wavelengths at a particular port. So this is why you see this white light coming here that has all the wavelengths coming in, okay? And if you don't have your acoustic wave here, you have different wavelengths coming out at different ports. This is just a regular demultiplexing device. But what we are interested in doing is to apply an acoustic wave in a way that for different times in this particular port here, it comes the green wavelength at some point, and then the red, and then the blue, and then the yellow, and so on and so forth. And we are reconfiguring the AWG as the acoustic wave goes on. And a very important thing is where you put the waveguides in the period of the acoustic wave. So you have to design that properly. These are pictures of the fabricated devices. We actually use two different approaches. One is with MMIs for the incoming and outcoming couplers, or these ones with stack couplers or free propagation region couplers that were designed here together with the group of Pascual Munoz and the VLC Photonics. And both devices work pretty well. So just to show you some results, these are what we expect for the response of our AWG. We have, for different ports, we have coming out different wavelengths. This is our experiment. It's not really perfect. Let's say the preset response. But if you go at that particular output channel and look what happens when the acoustic wave goes up, so you look at the light coming out at at the beginning, most of the light coming out of the output channel 5, okay? So there's no acoustic wave, light is just going there. You start to increasing your acoustic wave, this start to modulate, and some light is coming out of different port. And that are given power, you start to have light oscillating between basically 3 ports. This is not so clear here, but if you have a better detector in terms of time resolution, you can see what happens. These are for the two types of AWGs, MMI and free propagation region. And you see that the light, this is a period of the acoustic wave, and you see that light goes first in the green, and then goes to the blue, and then the purple, and so on and so forth. It more or less resembles well what we have for what we expect from our simulations. Okay, so in conclusion, I hope I could show that the modulation of photonic structures by source leads to novel and interesting physical phenomena. I didn't explain this very well, but these experiments for out-of-plane light gives reason to what we call the phonon-dressed photons and polaritons, and especially in the case of polaritons, there's a lot of interest and a lot of literature. A lot of people are investigating these systems right now. And there are also powerful tools to fabricate devices such as switches, modulators. I didn't mention pulse shapers and harmonic generators, but this is also possible, tunable multiplexers, and so on and so forth. Thank you very much for your attention.
Thank you, Mauricio, for your nice presentation. I think we'll have a couple of minutes for questions.
Thanks, Mauricio, for your very nice talk. I have one question. Most of your, well, all of your pictures and experiments and so on, they were based on the semiconductor materials. Mm-hmm. And at the beginning, you said that it would be possible to do it in soy as well. Could you elaborate on that?
Yes. Okay, in order to generate these acoustic waves, okay, you need to have piezoelectricity. Most of the work we have done is in gallium arsenide because this is the lab is expert on having gallium arsenide based material. But in the case of silicon, we have also some people working on that. So you have SOI, for instance, which is not piezoelectric, so you cannot basically generate the acoustic waves there. But if you deposit on a thin layer of zinc oxide, for instance, that is polycrystalline but has the C-axis oriented, then it's already piezoelectric, so you can put your transducers on top of this zinc oxide layer, remove outside it, and then your acoustic wave propagates without any problem. It could be aluminum nitride. There are many different piezoelectric layers that you can put on top of non-piezoelectric materials. Okay.
Hi. Thanks for the talk, Mauricio. Just one question. How this tuning mechanism compares with the thermal tuning mechanism in terms of power consumption?
Okay, the thermal mechanism usually is lower than this, so we gain on terms of speed, let's say. In terms of power consumption, what we think could be an advantage is that since you have this coherence of the wave, because the wave is coherent over the whole wafer. Okay, so you have 4-inch wafers. You have you know exactly the phase of the wave over the whole structure. So just with one transducer, actually, if you design it properly, in principle, you could modulate several devices at the same time. While in the thermal one, you have to heat every waveguide. In that sense, we believe the power consumption will be much lower in our case.
Thank you, Mauricio, for your presentation. I enjoyed it a lot. I just have a question. Have you considered other type of acoustic devices for your combination of photonics and acoustics? Why are you using SAW devices instead of other flexural plate waves or other kind of devices? Have you considered?
Yeah, you can use. From the technological point of view, the advantage of using surface instead of bulk waves is that most of the power is concentrated within one acoustic wavelength, so we don't lose. And most of the structures we want to modulate are also on the surface, so you don't lose the power that is modulating the rest of the remaining of the sample. But still, there are many other different surface waves or waves that are propagated on the surface. You can actually use a lot of them. In the case of photonic crystals, for instance, would be nice to have plate waves because you can have membrane. If you have a membrane, then it's ideal to have waves that propagate on the membrane as well. This is just for our convenience, let's say. But you can use different. I would go to bulk waves in the sense that we are going to lose a lot of power. But other than that, you can use many different.
No more questions? Okay. Let's thank Mauricio for his presentation again.
Okay. Now we're making a